seminar this week, and John Lee's going to be talking about the Nullstellensatz and its application to combinatorial problems.
Thanks, Adam. So first thing I want to say is that this is completely informal. I have notes, they're a mess. It's thought out, but what I'm trying to tell you is this is very informal. So if you want to stop me and ask questions, perfectly fine. If you want to leave at any point, like Pablo is sitting in the front here, sending the signal that he's interested. If he wants to get up after 1 minute and just leave because he realizes this is not what he expected, that's perfectly fine.
Microphone on, please.
Oh, the microphone, yes. Can everybody? But it's recorded, so that's why we need to.
We have to be serious. No mistakes.
Hello? Is it on? Good, excellent, thanks. Okay, so really, honestly, I won't be insulted. There's many talks I've sat through that were extremely interesting. There were many talks that were a bit painful, and I didn't leave because I felt that the speaker didn't expect that might happen. But I fully expect if you feel like this is not what you're interested in, that's fine. Okay. On the other hand, I'm trying to get you interested. I think it's very interesting in a way. So I want to talk about a modeling and solution paradigm for combinatorial problems. And many of us are used to paradigms for that based on linear inequalities. So we model our problem by 0-1 solutions, points in Euclidean space, and then it's very natural to try to capture those points through linear inequalities to write down the convex hull. And often that's because we're thinking about optimization, in particular optimizing linear objective functions, or sometimes maybe maximizing a concave objective function. It's often very natural to think about convex sets, linear inequalities, convex inequalities, because we're thinking about optimization. If we're not thinking about optimization and we're thinking about feasibility, like for combinatorial problems, does a design exist of a certain type? Does a Hamiltonian cycle exist in the graph? It's not necessarily more natural to think about inequalities, because inequalities, ordered fields, maximization, it all makes sense. But if we're thinking about just feasibility, it's just as natural to think about other systems, like polynomial equations. So I want to just talk a little bit more about the usual paradigm. Everybody here has different backgrounds. And talk about deriving certificates of infeasibility. And then show you a different paradigm to do that, and not just tell you what the paradigm is. The paradigm is a well-known theorem called Hilbert's theorem of zeros. Just knowing the theorem, if you try to apply it in kind of a semi-obvious way, it doesn't work that well. So what you have to do, like in all kind of applied mathematics, is engineer the theorem so that it is efficient. So that's the main focus of what I'm going to talk about. If you want to know the paper that I'm mainly going to talk about, it's called Computing Infeasibility Certificates. I'm not going to write the whole thing because I've had too much coffee. I'm a little jittery. But for combinatorial problems through Hilbert's Nullstellensatz, it's with Jesus de Loera, who was here for the first 2 weeks, and me, and Peter Malkin, who has joined the real world, and literally, because the systems I'm going to talk about are complex systems, so he's really joined the real world in more ways than one, and Susan Margulies, who at the time we started this was a graduate student with Jesus and now is at the, I'm not sure, some military academy on the northeast coast of the U.S.
She's at UPenn or something.
But that was last week. Oh. So she was at Penn State. So she was on a sequence of postdocs, and Penn State was the last stop.
So we just finished a joint paper.
Oh, okay, nice.
I communicated with her months ago, and somehow, she was.
Well, her email was there.
Non-military.
Yeah. So now she's off to maybe Annapolis or someplace like that. A permanent job. Permanent jobs get. Okay, the other person I should mention, there were actually 2 companion papers, and Shmuel Am was involved in the other paper, and Peter wasn't. But the main idea is actually from that paper, and then this paper is really about how to engineer the theorem to give good computational results. Okay, so let me take a step back first and talk about the usual paradigm of integer linear programming. So we talk about a really simple example. I'm thinking about stable sets in a graph. Oh, really too much coffee. In a graph G. These are just sets of vertices that are pairwise disjoint. That's a stable set. And you could ask for a graph, is there a stable set of a certain size? So you think about usually modeling this through 0, 1 variables. 1 if you pick a vertex, is 0 if you don't. You have just variables for the vertices. And so if I have a simple graph like this, a triangle, and I have a variable for each node, x1, x2, and x3, you have these very simple inequalities, x1 plus x2 less than or equal to 1, because that's an edge from 1 to 2, so you don't want both of these to be picked. So this inequality just says don't pick both equal to 1. And then by symmetry, you see that you have all the other ones as well. And say I'm looking for a stable set of size 2, so we're really thinking about feasibility problems, then I would write x1 plus x2 plus x3 is equal to 2. And you could stare at this and ask yourself, just look at the graph, of course, and say there's no stable set of size 2. The biggest stable set is of size 1. But you can certify this through what I would call a Farkish certificate, which just means taking combinations of these inequalities and adding them up. If for less than or equal to inequalities, you should take non-negative weights for the equation. You can take any weight at all, and you would get a valid inequality that's maybe more obvious that it's infeasible than the first one. So if I took these inequalities in this equation and weight them by 1, 1, 1, and minus 2, then I actually get 0 less than or equal to minus 1, which is my favorite obvious certification of infeasibility. And so this is kind of the Farkish paradigm of trying to show that a linear inequality system is infeasible, and that's Farkish's lemma, that, or some equivalent lemma, that a linear inequality system is infeasible if and only if there is is infeasible if and only if there's a certificate of this type. So that's all nice, but we're thinking about integer solutions, and so it's also useful to try to use the integrality in a system. And you can still do the same thing. If I'm thinking about integer solutions to that system, it still sometimes is a Farkish certificate, just like this. So I don't need to know that the system is integral. There's no real solution to this system. And so this is still a very useful paradigm. And you can find these certificates by linear programming. So let's look at another example before we really move to polynomials. Let's think about a bigger complete graph, K5. So let's do the same thing. So let's think about trying to show whether there's a stable set of, what's the biggest stable set here? It's of size 1. So let's think about these inequalities now. There's too many to write. There's 10 of them. Xi plus xj less than or equal to 1. And let's weight them each by a quarter here. Why a quarter? Because each variable appears in 4 of these constraints. It's one vertex with each of the 4 possible neighbors. So if I add all this up over these 10 inequalities, then what do I get? I get the sum of all the x's is less than or equal to 2.5. And that's kind of the biggest upper bound that you can get on the sum of these variables if you're not going to use integrality, because you can find a solution that makes that inequality tight. So if you set all the variables equal to a half, it satisfies these basic inequalities of formulation, but it makes that tight. So that means if you maximize the sum of the x's over this inequality system plus non-negativity, you're going to get that. So that's the best you can do. But then you say, hey, wait. These are supposed to be zeros and ones, so I can use the integrality, and now I can round this down and get 2. So I can see more. I can get stronger certificates by using the integrality, but not strong enough, because the biggest stable set in this graph is of size 1, not of size 2. So just using this certificate methodology of taking combinations, just like I did there in the linear case, and then rounding in an obvious way, you can't prove that the biggest stable set in this graph is of size no more than 1, unless you're willing to do this more than once. So if you're willing to derive inequalities this way and then apply the machinery over again, then you can do better. But that means iterating this. And so then you can talk about the rank of an inequality relative to a proof system. So this proof system of Farkash plus rounding is called usually Vatel-Gomery rounding. And so that's the proof system. And one round of it is too weak to prove that you can't have a stable set of size bigger than 1. 2 rounds is enough. So if you first take the triangles and prove for each triangle you can't have more than 1 vertex in a stable set, and then take those and do this all over again, it works. So that's how that all works. And I think many of you know this already, but I just wanted to set the context a bit.
Am I correct that there are examples which are showing that a lower bound for such a thing is exponential, right? So it's not.
Yeah, in the data encoding, if you take a really simple example in 2 dimensions of just a little tower like this, and you make an inequality like that, where the maximum in this coordinate direction is 0, and you solve the LP and you end up here, then you have what this system does is it takes an inequality and it pushes it, a valid inequality, it pushes it till it hits an integer point. And it pushes it till it hits an integer point feasible or not. So it'll catch these points, and you have to take another one and do that, and you have to work your way down. If it's t steps high, it'll take you t or 2t, I forget rounds of this. But the space to encode t is log base 2 of t, so this is exponential even in 2 dimensions. On the other hand, there are other proof systems for integer programming that take care of this in one shot. So there's something called disjunctive cuts, where I say, okay, what I can do is take the intersection of this set, so it's the set that's everything but this strip with the feasible region, and then it's just these 2 points, and I take the convex hull of that. And that cuts this in one step. You have to prove that you can find valid inequalities for the convex hull of 2 sets, but you can do it by Farkash, really. So even for a modeling paradigm, for different proof systems, they can have very, very different behaviors. Okay, so now we talk about a completely different proof system and modeling paradigm for stable set. And it's actually not a good one for stable set. So I'm going to really concentrate later on coloring problems, but just since we have this nice example for stable set, let's just see what it is. Lovász, I think, was the first one to talk about it in a serious way. So he said, why don't we think about these polynomial equations, xi squared minus xi is equal to 0. So this is just, x times 1 minus x equals 0. It's the quote-unquote stupid way of modeling 0, 1 variables. So you do this for all vertices of the graph. And then you have these very simple equations, xi times xj is 0 for every edge. So these are 0, 1 variables. It just says I can't pick both vertices that are the ends of any edge. So then if I want a stable set of size k, then I just have this nice linear equation that says the sum I equals 1 to, say, there are n vertices of xi minus k is equal to 0. So if you just in a very high-level way, a very naive way, try to compare this to what we did before, now we have equations instead of inequalities. Equations always seem somehow easier than inequalities, but they're nonlinear equations. If you're thinking about nonlinear programming, nonlinear equations is not a picnic. But we're not thinking about real variables here. We're thinking about zeros and ones. You're thinking of the symbols, if you want, that operate in kind of the usual additive way. So that's a system that Lovász actually, I think, first thought about in a somewhat serious way, and asked all kinds of questions about it, but didn't really pursue it very far, about how certificates maybe for this problem would behave. Are there bad examples, bad graphs where this doesn't behave very well? Of course there are bad graphs. This is, you know, an NP hard problem. So all these things are doomed to fail in a way, in a theoretical way, if P is not equal to NP. But I take the operations research viewpoint that, of course, it's doomed to failure, but maybe there are nice, lots of large problems where it works. People do branch and bound. They do all kinds of things in OR for problems that you're doomed to fail on. Okay, so if I went with this and told you about the theorem I want to talk about and how to engineer it, we can prove that, and Jesus talked about this a little bit in week 1, I don't know how many people were here for week 1, that applying the idea I'm going to talk about to this system is doomed to failure. You can prove that there are graphs where this behaves very, very, very badly. Well, I haven't said what this is yet. But
Yeah, I was about to say, doesn't it depend on what axioms you include in your proof system?
Yeah. So I have to get to that. I'm still doing the warm-up part.
Oh, okay.
But yeah, so what I'm going to talk about would fail miserably on this. So I want to tell you another problem and model it in a similar but slightly more delicate way, and flesh that out, because that's where we actually had some computational success. So the idea where it works is coloring. So I want a proper K coloring of a graph G. So this just means color the vertices so that two vertices of the same color aren't next to each other. You could think of it as packing stable sets if you want. So each color class is a stable set. There shouldn't be two vertices of the same color next to each other. And then what I want to do is fill the graph in with K stable sets. So you can think of it as partitioning the vertices of graph into K stable sets if you want. So how to model it? The typical way to model it would be with integer linear programming would be with 0, 1 variables, where I would have a variable xij, and it's equal to 1 if vertex I has color j. So you'd have the number of variables would be the number of colors times the number of vertices. So instead, I'm going to talk about a different way where you capture the color in the variable. Now, people have done that as well. I could have variables xi, where xi is equal to j if vertex I has color j. And then the possible range for the variables would be integers from 0 up to k. That's a terrible thing to do.
If no color also. Undecided. If you start as 0.
That's another problem. I want to color everything.
From 1 to k.
Yeah. So that's a bad way to do it with integers, not just zeros and ones, because what happens is you catch integer points inside the convex hull of feasible ones. You catch integer points that aren't feasible at all. So for example, if I have this graph and I have this nice coloring 1, 2, 3, and then I try to also, I could color it 3, 1, 2. So those are two nice colorings, and if I really thought about these as points in three-dimensional space, if I take half of each, then I get 2, 2, 2, and that's not a good coloring. So I caught integer points inside the convex hull of feasible integer points. So this is not such a good paradigm. Integer programming that Farkish plus rounding can't possibly work on this. So we do it a different way, similar to this in a way, but with polynomial equations. So what I'm going to do is have equations like this: x, I, k, minus 1 equals 0 for every vertex of the graph. That is not a superscript, that's a power. Okay, so the way I'm modeling now is that every vertex has k possible values, and it's the k roots of unity. So now we're in the complex world, and this is a nonlinear equation. So it's xi to the power k minus 1 equals 0. The feasible solutions are the k roots of unity. Why not? Because we're not trying to optimize anything, so I don't care about ordered fields and inequalities and trying to maximize, so I'm just worrying about feasibility, and it's perfectly reasonable to use those symbols, the k roots of unity, as the ways to distinguish the k colors. So now I have to figure out a way to write down that two vertices that are next to each other shouldn't have the same color. And it's not as simple as this. And it's not as simple as some linear inequality. So let me just tell you what it is. Here's what we do. We observe that xi to the k minus xj to the k over xi minus xj. This should equal 0 when ij is an edge. So these are kth roots of unity. So this is certainly true, right? I'm raising it to the power k, and if it's an edge, then these should be different. So I have no problem dividing by 0. But I can re-express that pretty simply. What do? I just realize that that's the same as the sum L equals 0 to k minus 1 of xi to the L times xj to the k minus 1 minus L. And I set that equals 0. So you can work that out. It's very simple. So I'm going to write these equations down for all edges. And just a simple observation. If sometimes people cheat when they divide by these things that might be 0. If I look at xi equal to xj equal to some beta, not 0, and I plug that in here, what do I get? I have k terms here, and then I have beta to the power L, beta to the power k minus 1 minus L, so it's beta to the power k minus 1. And that's certainly not 0, right? These are kth roots of unity, that's not going to be 0. So this will stop you from coloring two adjacent vertices the same. Okay, so what could we possibly do with this? So here's our system that we're going to work with. These equations with these equations.
So is it because you want to remain within the polynomials? So you are taking this high power because you could have taken norms.
Yeah. Right. There's
right?
a lot of ways to model this, but then you need a proof methodology for these things. So polynomials, we have a proof methodology called Hilbert's Nullstellensatz. So let me write this down and write it in two different ways. I'm going to write, I don't know, Hilbert already, so I didn't write it either of these ways. But this is the textbook way, or let's call it the mathematician's way.
Excuse me, but Dima is right. If I write down the Euclidean distance squared, this is also polynomial.
Oh, yeah.
So
It might be a good way. We didn't explore other
okay, so
formulations. That's right, if you square it.
Maybe an inequality, though. Not equality.
you have inequality.
Then I can't use these kinds of variables.
Yeah.
No, but there is also a minimum. You can for sure write it as an inequality, right? Because there's a minimum distance of all the kth roots.
Yeah.
All the kth roots have a minimal distance to each other.
Yeah.
So there should be equality formulation too.
But you can only impose, in theory, you can only impose a condition that the variables are real. There's no such concept. So
No. I just require that.
So you cannot
How
write-
many distances can I have among all the
K
unit
roots of
roots?
unity?
K choose 2.
Yeah.
So
Right.
if I require it's non-zero the distance between two kth roots, then of unity, then I can write
That will
this.
not define the...
Yeah, but how?
You would end up with
The equation.
a non-equality, right? So
The product of all of them would be
must be non-zero.
would be non-zero, but you can calculate it, I think.
Well, I mean, a non-zero can be modeled if you add an extra variable,
But then you
right?
have many solutions.
That you cannot invert.
Conjugates. I mean, this
The
one
variables
goes
are
with
complex.
polynomials.
So even if
What?
you write a single
You have
equation-
complex conjugates when you use the norm. I think you just use
Yes.
polynomials.
This is another, but so you cannot write it as a real polynomial, as a complex polynomial. Complex conjugate is
Depends
no,
on
true.
if you write a
Okay,
single equation,
right. This is
you
this
have
is
no
the
way of
argument.
imposing the variables.
This is
are
the
here.
argument. Again, and the other argument is of course also that you get higher powers than here. You have here a degree of what?
We're not so
Okay.
worried. Yeah, I mean, you'll see that we have ways to fight the powers.
Okay, yes. In this
Like the powers
formulation,
should be.
yeah. Not in
Uh,
general.
No, no, not in general. You can't fight the powers. I mean, we're being filmed as the NSA. I mean, who knows? But we're being taped. I always forget. No, this is great. I mean, I'd like to talk about this more after because this is really what I'm hoping to do is provoke people to think about it in some other ways. I'm thinking about this in a very simple way. Yeah, let me write this down. Some of you know it. It's Hilbert's theorem of zeros. So it's about when systems of polynomials have zeros and when they don't. So here's what I would call the mathematician's version. If K is an algebraically closed field, like the complex numbers, so not the real numbers, and I have polynomials, G1, G2 through GS, polynomial equations. Oh, let's write it. These are polynomials. I want to be really careful about this because I'm going to write a different version of it and we can compare. So these are polynomials in these n variables with coefficients from K. Then the system, G1 equals G2 equals and so on through GS equals 0, so a simultaneous 0, has no solution. And I want to say where the solution should be. Now it's kind of obvious. It should be in Kn. So in this field, I should pick a value for each variable. If and only if there exist polynomials H1, H2 through HS. Where should they live? Same place. K of x1 through xn. Such that, here's the property. If I add up I equals 1 to s of hi gi, that should equal 1. In other words, the constant polynomial, 1. Right, but what's on the left is polynomials. So this means all the coefficients are 0 on all the monomials, and then there's just 1 for the constant.
Mathematicians' way would be to say that the variety of this ideal is empty. If not ideal.
So, no, that's completely right. So I'm trying to use the non-mathematical language, but have the exact same statement. When I write the engineer's version, it's going to be not the same exact mathematical statement. It'll be a more mathematical statement, paradoxically.
So it might be helpful for people to compare this with the Farkas lemma.
Yeah. So actually, I'm going to compare it to something else. So the Farkas lemma is about inequalities, and so you can't view that in a simple way as a special case of this.
But you are taking linear combinations of linear inequalities.
Yeah, but I want to compare it to something even simpler. Something that I call it Gauss's theorem or Gauss's lemma. I don't think anybody else calls it that. I think it's actually called a Fredholm alternative sometimes. Jesus calls it something else. So it's an example of something called a Fredholm alternative. Like a Fredholm alternative because that's a bigger theory. So you can look at a really simple system of polynomial equations, linear ones. Ax minus b equals 0. And ask when that has a solution. Equations, really simple. So, what this is saying is that there's a combination of these. So here's the combination, y transpose times ax minus b equals 0. And Oh, no. What this says is that there should be a combination that gives the constant 1. But now if you think about what that means, what that's saying is that y transpose A, that's the coefficients on x, that shouldn't appear here, right? Because this is 1. This is a constant. There's no x variable here. So that the only way that can happen is if y transpose A is the 0 vector. And if the rest of it, minus y transpose B, is 1. But that's the alternative of AX equals B. So AX equals B has no solution exactly when there's a y, so that y transpose A equals 0, and y transpose B is non-zero, which you could scale to be minus 1 there. So if you want to prove this, I don't know if everybody knows this, but they do, of course. When they do Gaussian elimination, and they get a row that's all 0 on the left, and they get a non-zero on the right, there's no solution to the system. And every time there's no solution when you do Gaussian elimination, it's because that happens. There's a row of zeros and a non-zero on the right. So that's really a special case of this. It's a very nice thing that for linear systems, these polynomials are really simple. They're constants.
This actually holds in infinite dimensional setting.
It holds, yeah, just like Farquhar is holding in all kinds of places that I don't live. Okay. So, yeah, in a second I'll do what I call the engineer's version of it, which is just exposing a little more structure. It's just staring at the proof and saying, well, you can actually do this, that, and the other thing. Maybe I'll leave that. This will be on the test, so I erase it. Okay, so let me come back to the engineer's version of this. Let me just say something. So if I have a system of polynomial equations, many people here know better than I do, there are other approaches to trying to find a solution, like Grubner basis methods. There's also a Lon-Tarsi method. There's other methods. And we've actually compared what we did to some of these other methods, and it seems to be very good for the kinds of problems we're looking at. So we mainly did our experiments with coloring problems. That's very special. And on graphs that are nasty for integer programming methods, which means a lot of symmetry, which we somehow take advantage of. We also, you'll see, there's this curious combination of pessimism and optimism in what we do. So the pessimism is we look at systems that we expect are infeasible. Somehow it seems very pessimistic to write down all this modeling and it's always infeasible. The optimism is that our heuristic methods work. Somehow that seems to be the fit for these methods, for infeasible systems. If you really wanted to build something that took as an input a polynomial system for a combinatorial problem, and you didn't know whether it was feasible or infeasible, you need to do more than just this. This works really well for infeasible systems. If you don't know, or you expect it might be feasible, then you should be hybridizing maybe Grubner basis methods or something like that. So this eventually, if it's useful for systems where you don't know anything about their solvability, this would just be a piece of the whole methodology. Okay, so let me tell you, it's sort of shockingly embarrassing what the heuristic is that we use, our starting point. So what we do is we stare at this and we say, let's hope we're lucky. Let's just be optimistic. You know, the world is sometimes a good place. Sometimes the gods are smiling on us. So what we do is we say, okay, we're looking for these polynomials, h. So why don't we just pretend we're in the best of all possible worlds and assume they're linear? So then what we do is we just write down, so I say, let's just hope that linear is enough. Which is already, I think, in some ways the philosophy of engineering in a way, that hoping that linearization is enough. So here, of course, it's a little different, but we just assume that we're going to get lucky, and we write down linear polynomials. So in these n variables, we don't know what the coefficients are, so that's for I equals 1 to s. And then we just see what we want. What we want is that the sum I equals 1 test of hi gi is 1. So think about, I'm not going to write down an example. Let's just think about what's going on here. I've got these linear polynomials. I don't know what they are, but I'm hoping they exist. And I don't know what the alphas are that specify them. But I'm just going to see what the expressions would look like if I go and try to write down this certificate, this Nullstellensatz certificate. So what I do is I take these h's with the alphas unknown, I multiply them by my input polynomials, I add it all up. And what do I have? I have polynomials again, because I took linear things times polynomials, I have polynomials. Polynomials are made up of a bunch of monomials. Each monomial has a coefficient. The coefficient, when I gather things together, the coefficients are linear in the alphas. I want all of them, the coefficient for every monomial to equal 0, except I want the constant to be 1. And that's also linear in the alphas. So I have a big linear algebra system to solve. I want a bunch of linear expressions in the alphas, the coefficients on each of the monomials to be 0. So I want this constant polynomial of 1, and I just want the constant term, which is also linear in the alphas, to equal 1. So it's a huge, potentially huge linear algebra system in the alphas.
So linearity is not really needed here. You can do it in any degree.
Yeah. And if we don't live in the best possible world, maybe we live in the second best possible world. So then I would go to the next step and I say, okay, linear didn't work, but I still believe that my system is infeasible. So now I try quadratic. So I write down a much bigger polynomial for each I that's quadratic in these n variables. So it's the n squared coefficients, roughly. And I play the same game. I have a bigger linear algebra system, and I try to solve that one. And I just keep going like this. Now, I don't have to really make every hi quadratic. I can look at my model and decide what makes sense. So the mathematical version of it is keep increasing the degree of these trial certificates and solve this huge linear algebra system. This doesn't go on forever. Because these things exist, and there's bounds on how big the degree has to be. Horrible bounds on how big the degree has to be. But it's a finite algorithm.
Also look for certain sparsity pattern in the monomials and allow for high degree monomials, but few of them.
Yeah. I mean, we concentrate on coloring and so could we tailor it? Could we only put bigger degrees on some of them? But yeah, you could say it's quadratic, but not everything, right?
Yeah, exactly.
Who knows? So I think a lot of this puts much greater demand on the person who's modeling the system. I mean, of course, maybe you can automate this all 130 years from now. But in the short run, if you actually want to try to use this, you have to really start to understand your system and the graph that's input to it and try to figure out how you can make this reasonable. Now, what we discovered is for almost every graph we tried, linear works. And we don't know why. But we can find bad examples where the degree grows. It's not easy. They seem a bit pathological from the point of view of graphs that you can find on the street. But if you go to like the Dymax, this computer science center in New Jersey, had a challenge, 20 years ago, and they had all kinds of huge graphs, coloring instances. We can solve lots of their problems in degree 1 certificates like that. And these are some that they couldn't solve at all. So somehow, I'm not saying this will solve every problem. It can't, because P is probably not equal to NP. But somehow, these methods are quite orthogonal to other methods. And they seem to be a great complement for these other methods. The huge challenge that I see is how to integrate these methods. And it seems impossible. It's not in any obvious way. You've got inequalities in real variables, you have polynomials in complex variables. How are you going to put these things together in a reasonable way? That would be great if somebody has an idea about how to do that.
We have a quantitative estimate about the frequency? We have a quantitative estimate about the frequency of these rare graphs?
No.
1
Oh, I mean,
in a million?
they don't occur. I mean, we work very hard to find bad examples, like a sequence of graphs where the minimum degree grows, and we found a few, but
So in random graphs, it would never.
Oh, so here's part of the problem that so we applied this to 3 coloring mostly. And so we're trying to see whether a graph has a 3 coloring or not. And try to find graphs that don't have a 3 coloring for a non-obvious reason. It's not so easy. Like if there's a complete graph on 4 vertices, that's an obvious reason. So that's what we were mainly looking for, graphs that don't have an obvious reason that they have no 3 coloring, but don't have a 3 coloring. So where do you find graphs like that? You can't just find them by using integer programming methods because they don't work so well. So then you have to rely on prowling through papers where people prove that this class of graphs has no 3 coloring, but it has this kind of degree and it has this kind of girth, and people write papers. And so those things are constructed by gluing things together always.
Exactly, you can
And-
do products also.
Yeah, and then you wonder whether these things that are built by gluing, there are other kind of more disjunctive methods that would show that these things don't have coloring. So we looked where we could find, and there don't seem to be a lot out there, but there's probably many, many, many. We just don't really see how to generate them in a way where we can be sure.
Do you actually work over infinite field, or
No,
you can do it over?
That's coming. Yeah. Yeah, so that's part of the engineering. So that's what I want to turn. So that's the heuristic. And yeah, there's all sorts of bells and whistles about increasing the degree in a non-uniform way by leaving out terms. So lots of ways to play there. Okay, so for some people, all this algebraically closed stuff, they know what that means. Other ones, are just being quiet and hoping nobody, asks them. I won't put anybody on the spot. So here's the deal. So, the real numbers, they're not algebraically closed. The complex numbers are. But you can take the algebraic closure of any field. And, for example, the algebraic closure of the rationals is the real numbers. What we're going to do is just look at 3 colorings, our simplest interesting example. And I'm going to write down the system again just for 3 coloring, but not over the complex numbers. I'm going to write it down over the field on 2 elements. So nice binary arithmetic. So let's think about the field on 2 elements and 3 coloring. So what I'm going to write down is xi cubed plus 1 equals 0 for all I in big. Now, this is not, there aren't 3 roots of unity in F2. Okay, so I have to take the algebraic closure, but the system I write down, the coefficients are going to be in F2, the binary field. But I'm going to look for solutions in the algebraic closure of F2. So what's the algebraic closure of F2? One way to think about it is you look at all of the finite fields of characteristic 2. So 2 to the different powers. And you take the union of all those. That's the algebraic closure of F2. That's one way to think about it. So that's where we're going to look.
But isn't it enough to look at in F4?
Maybe. We didn't think about it. Well, it may be, but we want to use the Nullstellensatz, which refers essentially to closed fields. So I don't know if that will work. You could write the model, but I don't know if the exact proof machinery is true anymore.
Yeah.
No, but that's an interesting idea to pursue that direction. Somebody should write all this down. It would be yeah.
I'm a bit confused about something. It's my lack of knowledge of algebra. Why can't you set xi to be 1 in that equation? Why does that not work? Because aren't you taking it more to those 2?
So 1 is one of the roots.
Oh, okay.
So the roots are going to be 1, alpha, and alpha plus 1, where alpha squared plus alpha plus 1 is 0. So what I'm going to do is just do algebra with these alphas, but I do the coefficients mod 2, because they start with the binary field. So these are my colors now, 1, alpha, and alpha plus 1. I just keep this relation in mind, and I work with my equations, and I do the coefficient arithmetic in the binary field.
Well, I get a feeling that F4 there should be enough, but well, okay.
Yeah, but I don't know. Maybe it
It's
is.
offline.
Yeah. Maybe it, so. Does that work in F4?
I mean, yeah. I mean,
if
just
you
as the
have-
degrees will be high, right? I mean, so you cannot.
But is there always a polynomial certificate of infeasibility for non-algebraically closed fields like this?
But you have the equation which says that each element is actually in F4, so it really does not make a difference. So it does not make a difference, you know, because your equation says that each xi.
So I haven't written down all my equations yet. So tell me if it's still true.
No, that's. I mean, you have a Z and a Z on the right hand side, which are a bit trickier, right?
Yeah, but you already know the solution of that. So the other equations are more.
So and these are my edge
All right.
equations.
Yes. Okay.
No.
Correct. So because your x's must satisfy x cubed equals to 1, then you are in F4. Full stop.
Okay, but I have to do my arithmetic in F4, not in this field. So is this the right equation, or is there another equation in F4 for the edge equations?
This is in F4. Why not?
So you can confirm. I mean, I can't think online. But if I view these numbers in F4, is it still the case that every solution of this really corresponds to a coloring, and every?
I think Marcus said it doesn't make
So
any
it
difference.
doesn't make.
It's just
really
symbolic.
Matter. It doesn't matter. I mean, it's your solutions are automatically in
Yeah,
F4,
yeah.
but I don't
But
understand.
only
This
yeah.
is no problem. I mean.
No, you're right, because
algebraic closure. It's
yeah, and the coefficient. I mean, it's still characteristic too, so the coefficient arithmetic is the same.
if you are in this algebraic closure or in this finite subfield, doesn't really matter. I mean,
Yeah, because I'm in the finite subfield, it doesn't matter. Which, as I said, it is the union of all these
Yes.
these characteristic two fields. So yeah, you could see it that way. Right. That's right. That's a good point.
But let me as a non-algebraist understand the discussion. Does it mean that we can apply the Nullstellensatz for showing?
Well, you can apply it for sure because the way I write it, it's an algebraically closed field by definition. So you can definitely apply it.
No, but working in F4 instead of the closure of F2.
Yeah, but I mean their point is.
There are polynomials over the field F4 in n variables such that this holds or not? I want to understand the discussion from the audience.
So you mean for any? So do you mean is that theorem true for
Yeah, you need it. or
finite
not?
fields?
It doesn't make any difference because you're already constraining the solution to lie in a nice.
in
but
general,
you want to
Yeah.
have
So in general, it wouldn't be
you want
true.
to
If my
find-
coefficients were arbitrary numbers in the algebraic closure of F2, then it wouldn't make sense to write this in F4. But I mean, this is a very special system where the coefficients I'm going to take advantage of this are in F2.
The question is, where do the h's come from later?
Exactly.
the h's you can always take in the field of
Yeah, yeah.
of your
Right.
polynomials you start with.
So that's part of the
Unless-
engineer's
regardless
version.
whether they're closed.
Yes.
or not.
Yeah.
And this shows his argument showed this because he showed that it's a linear.
It's always linear,
for
so
each fixed degree it's a linear system,
Yes.
and if you can solve a linear system, you can also solve it in the same subfield. You know.
you're
So-
stealing my talk.
Okay.
But no, that's the point. Is
So algebraic closure
that argument?
any role?
What?
Algebraic closeness does not play any role.
It doesn't exactly. So let me write down what I call the engineer's version, and you can see the difference, and it's just what he just said. Here's the engineer's version. I say this a little playfully, of course. So I take any field, and G1 through GS are polynomials with coefficients in that field. And I ask the question whether the system G1, G2 through GS equals 0. I ask whether this has a solution in the closure. So this has no solution the algebraic closure, if and only if there exist polynomials. And here's the point, they're H1 through HS. Where do they live? They live in K, not K closure.
Okay,
of
this was my
X1
question.
Such that same thing, sum I equals 1 to S of HI, what do they call them, GI, should equal 1. But actually I don't have to even put 1 there. I could put a different monomial. Some other monomial, if I
Some
want.
non-zero constant.
So I put a fixed monomial. And that's also a certificate. And that's just another little, very little trick that's actually useful.
And if K were not a field but a ring,
Wow.
then you cannot solve linear equations.
So you said if K is not a field but a ring.
Oh, because the idea is basically what I understood from Marcus is that you solve linear equation systems
Right,
by
right.
separation.
Yeah, so then you
And then you cannot
have to divide.
If you-
No, ring is not enough.
Right.
But a fixed monomial you need some hypothesis. Otherwise, a fixed monomial would not be enough. Right?
Yeah, you have to look at the model and see if that works. But so yeah, maybe I should just write 1.
Oh,
But
you have, sorry, that I insist on the ring question, because if you have a monomial here, or you can also have a fixed polynomial. Why not? Non-zero.
but I have to
no,
make
no, no.
sure that it's non-zero.
You need
The
just
idea
an
is
integral
to have,
domain.
you have a denominator on the left-hand side, which you can move to the
Yeah,
right-hand
yeah.
side. This was my very vague idea. It doesn't work.
So just to make this concrete, I've got a set of polynomials in the rational, with rational coefficients, and you're saying I can prove I can certificate that there is no complex solution using only rational.
Well, so let's be careful. So the complex is not the algebraic closure of the rationals; it's the closure of the real.
You could take any algebraically closed
Yeah, any
extension.
right, right, exactly. So yeah, if the coefficients are in the rationals, and you're looking for solutions over the complex, then you can as well just solve linear systems over the rationals. In other words, the certificate would be a rational polynomial
So the
certificate.
algebraic closure of the rationals, is that just the complex numbers that have got algebraic components?
Yes.
Yeah? Right, okay, sorry.
Q plus IQ.
Yeah, I think I actually said something wrong before. I was thinking. Okay, so yeah, I want to make this a bit more concrete. So probably now everybody has checked that if they plug in 3 distinct values for 3 vertices, that those equations are satisfied. So I plug in for x1, 1, and for x2, alpha, and for x3, alpha plus 1. So say it's a triangle graph, you can check that those equations are satisfied. Okay, so does everybody see what the algorithm is now? So I have an input graph, I write down the system. The coefficients are in F2, they're just zeros and ones. I'm looking for a solution in F2 closure. I'm only really interested in graphs that don't have solutions, so in a way it doesn't matter so much where I'm looking. But the certificate is going to be I construct that big linear algebra system. The coefficients in that linear algebra system just come from these coefficients. So they're just zeros and ones. And so if I get a certificate of infeasibility, though the degree 1 certificate, the linear polynomials can only have coefficients that are zeros and ones, so they're not in this closure. So nothing I do when I run the algorithm involves whether it's F2 closure or GF4, it doesn't matter, right? Everything I'm doing is just in the binary field, these linear algebra systems. So this closure, whether it's the four element field, all of that is just a way to, yeah, I don't need this, understand what you're looking for if there were a solution to the system. Okay, so that's the basic idea. That there's a huge, I'm not going to show tables because
Could you please just for me, dummy, write an explicit formula for the closure of F2? Is it like the
formula for it?
Yes.
No.
Or describe it?
Well, I'm waiting for the
Dummies.
No, not for the whole closure. No, I don't want to do that. No, because it's an infinite field. It's the union of all the finite fields of characteristic 2.
Okay, so it's a union of F2.
Of GF2, GF4, GF, yeah.
That's easy, that's what I want.
I said that. There's a tape, I can prove I said that. Okay. But anyway, what I do doesn't involve the closure. It's just I solve linear systems over the 2-element field. So now we start to try to engineer this a bit more. And the first way that we found really useful for real graphs is to add redundant polynomials. Okay? So these are extra equations that are satisfied by all the solutions that have the potential to decrease the degree of the certificate. It can't increase it, because I could always put a coefficient of 0, a weight of 0, on redundant polynomials. And people like Adam is sitting there, he's Mr. Integer Programming, he says, yeah, we had cutting planes. These are inequalities that are redundant for the integer solutions, and they help us a lot, because they help us generate Farker certificates without rounding. Or rounding in an analytic way rather than a computational way. So here are some useful ones for graph coloring. So again, we just focus on this really small graph, which sits inside lots of bigger graphs. And we write down this simple equation, x1 plus x2 plus x3 equals 0. Okay, so you can check that if you plug in 1 and alpha plus 1, it's satisfied. Right, because you're doing the arithmetic over the 2-element field. So just add up those 3 numbers. You get 2 alpha, which is 0, and you get 2, which is 0. Okay, so that's a redundant equation. If there's a triangle, I write down that equation. That's useless, actually. What's useful, and again, this is just engineering, is to put squares here. And it's still true, those squares of those numbers are all distinct. And when you add them together, you also get 0 again, because they're all distinct. So those are redundant equations that you could also add. Those are really useful. So if you have a graph and you're trying to apply this whole method, and you got a degree 4 certificate and it took you days, you put these in for all the triangles in the graph. It's not so many extra equations. And then you're going to have a degree 1 certificate in many, many cases. So we have examples that took 4 hours, big graphs, 1,000 vertices with this system. And then and a degree 4 certificate took 4 hours. And then we add just these extra equations as a degree 1 certificate. You get it in less than a second, 0.2 of a second. So figuring out what redundant polynomials to add can really improve the performance. Just like in linear integer programming, figuring out what cutting planes to add can drastically improve the performance. But this, puts a huge burden on the prover, the user, to figure out what equations to add. For graph coloring, these are really useful. Somehow the squares here nicely balance the quadratic nature of these equations. And so you get this nice cancellation somehow. It's the right balancing act. So that's a trick. So I don't have a general trick. I just know that for lots of systems, it's very helpful to add these redundant equations. You can try.
John, it's not true for any fixed power?
We don't have so.
But you just look at the low power.
Yeah, so you could put bigger powers, but I don't think it's the right thing to do.
But taking square is a field automorphism here, so that's why you can do it, right?
Yeah, but I mean, I don't want to take the third power because that's not going to work. But
But some other powers would also work.
yeah, and so for K coloring, we thought about that a bit. What's the right power for K coloring? And one of us, not me, thinks K minus 1 is the right power. I think square is still the right power. Because still, well, I don't know. No, maybe he's right.
Can you do something clever for any odd cycle like that?
Yeah, we tried these kinds of things for odd cycles, small complete subgraphs. We tried these kinds of things. The system gets bigger as you add these things, but you want to do anything to avoid going to a higher degree. Just like in integer linear programming, you're going to do anything to avoid branching. So if you can cut and make some good progress on some measure, then that's what you should do. It's a mild exaggeration of the integer programming analogy, but it's roughly true. So let me tell you another thing you can do. So again, I come from the integer linear programming world, so I think about what tricks there can we somehow see analogs of here. You can also, in integer programming, you solve a linear program sometimes, and you see, because of a very extreme situation in something called a reduced cost, that you can fix a variable at 0 or 1. So you could ask, well, what are there situations here where we could fix variables? And coloring problems, you could definitely do that. You could pick one vertex and say, well, that's going to be color number 1. And if there's an adjacent vertex, I could arbitrarily call that color 2. And if there's a triangle, I could fix the 3 colors on that triangle. Here, you've got to be careful because of the engineer's version. If I fix one variable at 1, my linear system is still over F2. If I fix another one, I have to pick alpha or alpha plus 1 if it's adjacent. Now, all of a sudden, I'm not doing my arithmetic in F2 anymore. I'm doing it in F2 closure. But I'm doing it, with that rule that alpha squared plus alpha plus 1 equals 0. And there's more symbols, so, I don't think most people have a code sitting around that can do linear algebra over, this field. So I think that's something to avoid, trying to fix variables like that, even though that's a very typical trick in integer linear programming.
Well, I mean, in cryptography, there are people who have this code.
Ah, okay.
So you don't...
Yeah, and they're actually filming us right now, so it's true. Some of my best friends that are protecting all of us. So let me tell you something else that's also typical in integer linear programming, and in a way gets around this fixing overhead. So it's what's called branching, which normally you try to avoid, but sometimes you do it. So say I do everything I said. I add these triangle inequalities, squares, and nothing is working. I can't get a degree 1 certificate. I try for degree 2. I don't see that. Degree 3. I don't want to go degree 4 because I don't want to buy a bigger computer. So it's just like an integer linear program. You say, okay, I'm going to branch. I'm going to create subproblems. So how do we do it? What we do is this. We suppose that one of our polynomials factors and don't forget, I'm looking for a solution where all these are equal to 0. So if I want this to equal 0, either that's going to equal 0 or that's going to equal 0. So I can make subproblems. So here's my original system, F1 through Fs. I make 2 subproblems where I have F1 through Fs and G1, and then another one where I have F1 through Fs and G2. And I just now endeavor to show that, that these are infeasible. So, example.
Sorry, you keep the F. I cannot read the indices.
So I don't need, I keep the whole system and I add either this equation is 0 or that's 0. They can both be 0.
Yes, but you can drop the Fi or whatever this index is.
But it could change the degree of the proof, no?
Well, maybe I could, drop just the I, not all the other ones.
Oh.
Yeah, right, I could drop
So
just
the question is, when you branch like this, do you add to the list or do you replace?
I think you could do it by replacing. We may have stupidly not replaced. Yeah, we may not have. Yeah, I don't know in our code, even if we tried this actually. So let me show you an example of this for the coloring, the 3 coloring. And I'll stop soon. Clumsy. Can't blame me for talking anymore. So we use the fact that xi cubed plus 1 is xi plus 1 times xi squared plus xi plus 1. So you can check. Not cheating you. So that's a possible way to branch. I think we did a few of these by hand, and it worked pretty well. Okay, so, and these are, the coefficients are in F2. So that's a better thing to do than some kind of variable fixing. you don't get into this trouble. So branching, that seems to be useful. You can do multi-way branching. So instead of two terms, say it doesn't even have to be a polynomial in the system. It has to be in the ideal generated by those polynomials. If I have anything in the ideal generated by the polynomials, and I can write it as a product of S polynomials, I can make an S-way branch. Not S, not that S, K. No, K something else. T. So you can do that. So the last thing I'm not going to talk about, I'm just going to say it. So we're working right now on using symmetry for these graph problems. And the way we exploit graph symmetry is in the linear algebra system directly. So the graph symmetry forces some symmetry in the linear algebra system, and we take huge advantage of that. And so we're running lots of problems now, and we should have good results to show soon. So this is not a toy system. You can really prove that a graph has no three-coloring with 1,000 vertices and several thousand edges. And it's really competitive with any other method, and probably better than any other method for infeasible instances. So it's not just kind of pie in the sky. We have formulations for other problems, for Hamiltonian Tor and all kinds of problems that we haven't experimented with. So I think there's a lot of room to try this more, but you can see the kind of demands that it puts on someone who's trying to make this work. You have to figure out redundant equations sometimes to make things reasonable. The modeling is not so obvious sometimes. So I don't think you'll find a lot of undergraduates that you could teach much of this to, because they need to know some math and some modeling, and often those communities kind of diverge. Anyway, that's what I had to say, and please work on this and better these results.
Thanks very much, John. Anybody got any more comments or questions?
So in your code, do you use something off the shelf, or you?
So I've never been in the code myself,
Okay.
but I've talked to people who have, which is Susan Margulies and Peter Malkin. We tried to use for the linear algebra something off the shelf, and we're not successful, and then we ended up writing our own. But I think we need to go back to doing something, much more efficient that's off the shelf. So we don't do it in a completely straightforward way. We found some good way to do. Somebody who described a good way to do the arithmetic, over the binaries. But I think that probably we can get an order of magnitude improvement by doing the arithmetic in a more well-disciplined way. These are huge systems, so paying attention to issues about caches and worrying about you sort of have to start worrying about the hardware when you're talking about systems this big.
I mean, you would worry about bits. You want to encode everything in bits rather than in.
Yeah, that for sure. And then a few years ago I worked at IBM, and we had this Blue Gene supercomputer, and I tried similar kinds of things, not exactly this idea, but similar craziness on this huge parallel machine that doesn't have a lot of memory per node and has a certain kind of communication pattern. And it was terrible because each processor is kind of slow, and what's fast is floating point arithmetic, not logic. And so
But you can actually use that floating point.
they use the floating point processors in a.
A LAPAC that is built in, that is provided by the system, actually can operate on bits, right? Why not?
Yeah, sure.
That's what people do, I think.
Right.
This would
Yeah,
be
so we don't, I'm pretty sure in our, software stack, we don't really have the, I would say, a state-of-the-art implementation of the linear algebra. And that would be great to plug in.
I might not be the right person to ask this question, though.
Somebody else want to ask?
Ask the question, and then you can, either of the member of the audience can correct or verify this. So when you're saying you are exploiting symmetry in graphs, how does it work? You first you try the linear
No. So we look at the graph, we find the symmetry. If it's, you know, like
And
vertex
then can
transitive
you
or
still
something.
try to solve the linear
Not right
system?
away. No, we don't write down the full linear system. We find a smaller system that has a solution if and only if the system that you don't want to write down has a
Like
solution.
polynomial system.
No, the linear algebra system. So we pass the symmetry through the polynomials to the linear algebra, and then we look, what's the symmetry now in the linear algebra system? So we don't really write it down, we think
Yes.
about what it would look like, and then we write down a
So
smaller
you said
system.
the general paradigm is you start with linear factors hi, and then try several.
Yeah. So we imagine what the linear system would look like, and then we make it smaller using the graph symmetry. If that doesn't work,
Yes.
then we imagine what the linear system would look like for degree 2 and use the symmetry there.
But general degree 2 for all the factors, or do you
General.
symmetry to select certain?
No, we haven't tried that. That would be a good thing to try, but we haven't. The other thing I should mention, I have many good reasons besides the stable set problem for thinking that if your variables are 0, 1, this is not a good way to go. That this is really good for things like k-coloring, where you can pack a lot of information into each variable. I think that's one thing I believe, based on a small number of examples. So we have formulations for Hamiltonian Tor and things like that. They're probably the wrong formulations. They're formulations where, you know, it's 0, 1, 1 if you pick an edge in the Tor, and probably what you want are the permutation formulations, where variable xi is equal to j means that that vertex j follows vertex I in the Tor. And if you could write a system down for that, I bet this would work pretty well. You spent a few years, you know, tuning it.
Any more questions? Okay, let's thank Tom again.
Great, thanks a lot.